Hello guys, I hope you all are doing good. I am Vaishali Kikan and we are discussing the electronics engineering. Today in this video, we are going to talk about the rectification property. So we are discussing the applications of the diode, and today we are going to start the first application of the diode, that is diode as a rectifier. What is a rectifier? What is a half wave rectifier? What are the various characteristics associated with the half wave rectifier? All of these things we are going to see in this video itself. So I hope all of you are very excited to watch the half wave rectifier and to understand it thoroughly. Right, I have already discussed about the series and the parallel configuration of the diode. I hope you all have watched the previous video itself. Now coming to the half wave rectifier. What is the half wave rectifier? What is the rectification property? In our daily lives, in our appliances, most of the time we are using the DC current, but what is the current that is coming to our houses? That is the AC current. So we require a rectifier which will convert the AC current to the DC current. So rectifier is a device which is going to convert the AC current to the DC current, or even it can convert the AC voltage to the DC voltage, right? So both of them are the same thing, right? So rectifier is a device which converts the alternating voltage or AC voltage or current into the direct voltage or current due to the certain type of non-linearity of its characteristics. We all know the diodes are having non-linear characteristics. We talked about the current equation of the diode, which was having the exponential term, and also the voltage equation of the diode, which was also having the exponential term. So I can say both the current and the voltage equations are non-linear. So I can say the diode characteristics are non-linear. Right, so this is the circuit of the half wave rectifier. Now we have two types of rectifier, half wave rectifier and full wave rectifier, right? So in the full wave rectifier, we are going to talk about the bridge rectifiers as well. So we are starting our discussion with the most basic type of rectifier, which just require only one diode, right? And this type of rectifier is the half wave rectifier. I require only one diode over here. So you can see we have the 230 volt and 50 hertz supply to the given transformer. Now here the transformer is a step down transformer. What is the step down transformer is doing? Step down transformer is going to reduce the voltage at the output. So at this terminal I will be having very less voltage as compared to this terminal, because 230 volt, if the 230 volt goes to the diode will be getting damaged. To protect it from damage, I will be using a step down transformer. So with the step down transformer, here I will be having some input voltage at this terminal of the transformer. Because of this voltage, here some voltage will be induced, that is VI, right? So because of VI, the current will start flowing in the diode. In the same manner, the current is coming into this terminal of the transformer. So current is coming into the AC form, and the current will move in the AC form towards the diode. And here after the diode, I have connected an RL, the load resistance, and from the load resistance I will be calculating the V out, right? The output voltage, or we can say it's the VL, right? So you can call it VL, the load voltage, or the output voltage, anything of your interest. Right, so here the TF is a step down transformer, and here we have the DC resistance of the winding. For this winding I have the DC resistance which is represented by R2, and we have some forward resistance in the diode as well, which is represented as RF. So even R2 and RF are very small, we can neglect them in the future, but as of now we are considering there are some forward resistance and DC resistance of the winding, right? So this is all about the circuit diagram of the half wave rectifier. Now moving towards the operation of the half wave rectifier, how this circuit is going to rectify, how this circuit is going to provide the DC output from the AC input. So how this thing is happening, we are going to understand the operation with the help of these two circuits. These two circuits represents the diode in the forward and the reverse bias condition. So now we are supplying the AC voltage. Now when the AC voltage is passed through the diode, AC voltage means it's a sinusoidal voltage. For some instant of time it is positive, and for some instant of time it is negative. right? And we all know diode is a unidirectional device. It is going to transmit the current only in the forward direction, right? When we are making it forward bias, it will be acting as a closed circuit, right? But when we are making it reverse biased, we are connecting the opposite polarity of the voltage, then it will be in the reverse bias, right? So when the reverse bias would be there, the diode will be behaving like an open circuit, right? And when it is in forward bias, diode will be behaving as a closed circuit. So this is the thing which is telling me the diode is unidirectional. So circuit utilizes the unidirectional conduction property of the diode to provide the DC output from the AC input. So current flow through the PN junction only when it is forward biased and is completely blocked. Here I am not considering any leakage current, right? So you will be when you are doing the practical calculation, you will be seeing that there is some very small amount of leakage current also there, but I am not considering it. So I am saying that I have completely blocked the current when it is reverse biased. So AC main supply voltage will be having the positive and the negative half cycles. I am going to show you the waveforms as well. And now when we have the positive half cycle, at the A terminal I will be having the positive and at the B terminal I will be having the negative. So this means I have the positive half cycle, and you can see when I am sending the positive terminal over here, positive is connected to the P terminal of the diode. This terminal is the P terminal of the diode. So when the positive is connected to the P terminal, I will be having the forward bias. So in the positive half cycle, my diode will be forward biased and it will be behaving like a very low resistance device, right? So it will be behaving like only the forward resistance RF. So it will be giving the path to the current. So the VL, the output voltage at this resistor RL will be nearly equal to the input voltage only, because here I am not having any voltage drop across the diode, right? So now I am ignoring the cut-in voltage of the diode, because the cut-in voltage is 0.7 or 0.3, which is very less than the maximum voltage, right? We are dealing with the 230 volt and we can reduce it to 10 or 20 volt, but 0.7 and 0.3 are very less as compared to the operational voltages that we have, and now we can easily ignore it. So we have ignored the cut-in voltage, and that time we will be having the load voltage is equal to input voltage, right? So we are getting the output when I have the positive half cycle. Now let's have the negative half cycle, and when we have the negative half cycle at the A terminal, I will be having the negative voltage, and when I have the negative voltage at the A terminal at the P, I have the negative. So this is the reverse bias, and when I have the reverse bias, the diode will be replaced as a high resistance device, and when it is giving me very high resistance, so it will be blocking all of the current, right? So current will not pass through here, and at the RL we will never be having any voltage generated, right? So this is the ideal condition. Practically there will be some leakage current or saturation current that is passing. We are ignoring it because it is very less, right? It is not generating much of voltage, so this voltage can be ignored. So we are considering that the load voltage in this case will be 0, and in the previous case it was nearly equal to input voltage. So this is the waveform in the positive half cycle. We saw this is the load voltage. So the maximum of the input voltage was Vm, and the load voltage is also having the same curve, and it is having the maximum Vm only, right? So it has completely blocked the negative half cycle. You can see we are not having anything in the negative half cycle, so output is blocked over here, and this is the reason it is called the half wave rectifier. It is just rectifying the half wave. It is going to give me the output, the positive output in the half wave only, right? So here you can see the current is also having the same variation. Current is also present in the positive part only, and in the negative cycle the current is blocked, right? Same like the voltage. So here we will be having the diode on condition, here we will be having the diode off condition, and the output voltage will be pulsating in nature, but now the magnitude is changing in the positive direction only. You can see we are not having the complete DC output. For complete DC output we can use a capacitor in combination to this circuit and we will be getting complete DC output as well. But as of now you can see the output is pulsating, but these pulses are present only in the positive direction, and this is the advantage of using the rectifier. So I hope you understood. So now coming to the rectifier operation, these are the various rectifier parameters that we have to understand. First of all, the input voltage. The input voltage is the AC voltage which is represented as Vm sin omega t, right? So this is the input voltage that we have, and we are neglecting the drop across the diode. We are considering the forward resistance is very less. We are not considering there is any drop across the diode. So the load voltage will be equal to the input voltage, and the load voltage will be equal to Vm sin omega t. When we have the input in between 0 to pi, in the 0 to pi only we were having the positive half cycle, and when we were having the positive half cycle, the load voltage was equal to the input voltage, and in the negative half cycle, which was from pi to 2 pi, we were having the zero load voltage, right? So this is how I can represent the voltage equation at the load. The current can be represented in the similar manner as Im sin omega t when I have the positive half cycle, which means the omega t is in between 0 to pi, and in the negative half cycle, that is omega t in between pi to 2 pi, I will be having the zero current. Now what is I? I is given by the Vm also. So I and voltage, the current and voltage are related with the help of Ohm's law. So we will be taking Vm and I will be dividing it by R2, RF and RL. So R2 plus RF plus RL is the total resistance of the circuit, right? So RF is the forward resistance, R2 is the coil winding resistance, RL is the load resistance that we have, and in this manner I can calculate the current. Now we have to calculate two parameters, the average DC load current and the RMS load current. We are going to talk about both of these things in the today's video only. We are going to talk about the next parameters in the next video, right? So first of all, let's talk about the average DC load current. What would be the average DC load current at the output? So what is the average current? Average value of any function can be calculated in between the limit, lower limit is L and the upper limit is U. So if you need to calculate the average, what you will be doing? You will be using this formula. So F mean or F average is equal to 1 upon upper limit minus lower limit 1 upon U minus L integration from L to U Fx dx, and this is how you can calculate the average value of anything, right? And we are using the same formula to calculate the average current. So L is the lower limit over here, U is the upper limit over here. So now we have to calculate the average current, which is also known as the DC current. So here we will be having the upper limit as the 2 pi and the lower limit is 0. So 1 upon 2 pi minus 0 would be 1 upon 2 pi only, and integration from 0 to 2 pi I d omega t. So this is how we can calculate the I average. So now let's put the value of I was Im sin omega t. So when I put I is equal to Im sin omega t, we will be having 1 upon 2 pi integration from 0 to pi only, because the output was in 0 to pi only, right? In 0 to pi only, I was equal to Im sin omega t. We can have integration from pi to 2 pi as well. From pi to 2 pi, the output was 0 d omega t. So 0 into something would be 0, and this is the reason we have completely neglected this term. So this term is not there. You can simply write IDC as 1 upon 2 pi integration from 0 to pi Im sin omega t d omega t, right? Now we just need to integrate. Im is a constant, is the maximum value of the current. We can take it out, pull it out. So IDC will be equal to Im upon 2 pi integration from 0 to pi sin omega t d omega t. So integration of sin omega t is minus cos omega t, we know that. So we can put instead of integration of 0 to pi sin omega t, minus cos omega t, and the limits are 0 to pi. So when you put the limit, IDC will become equal to Im upon pi. This is how we can represent. What was Im? Im was Vm upon Rf plus R2 plus RL. So this is how, in the terms of maximum current or the maximum voltage, I can represent the IDC. Im, I have already told you, Im was equal to, this is Im, this is equal to Vm upon R2 plus Rf plus RL. So I have just replaced the value of Rm, and this is how you will be calculating the IDC, where Rf is a forward resistance, I already told you, R2 is the transformer secondary resistance or the winding resistance, RL is a load resistance, right? So I hope you understood how we calculated the DC current. Now coming to the RMS current. So how we calculate the RMS value? What is the RMS value? RMS is the root mean square value. So we will be taking the mean, and then we will be taking the under root, and then we will be squaring all of the terms and adding them. So this is how we will be having the FRMS. We have under root, we have for the mean I will be taking 1 upon upper limit minus lower limit, and for the square I will be taking the integration from L to U fx square dx. So this is the root mean square. So take the root, take the mean and take the integration, and that we have to take square of the function. So now I will be taking the IRMS as 1 upon 2 pi integration from 0 to pi I square d omega t power 1 by 2. So what is I over here? I is again I am sine omega t from 0 to pi. So I will be taking 1 upon 2 pi from 0 to pi I am square sine square omega t d omega t, right? So this is how I will be calculating the root mean square. Now I just need to simplify it. Im is a constant, I can pull it outside. So if I pull Im outside, so here I will be left out with Im square upon 4 pi, and here because this 2 is also coming outside. Start again. So Im is a constant, we can pull Im square outside. So when I pull Im square outside of the integration, I will be having Im square upon 2 pi integration from 0 to pi. Now sine square omega t can be represented as 1 minus cos 2 omega t upon 2 d omega t. So this is how I can represent the sine square omega t, and the power is 1 by 2. Don't skip the power, right? So now here I will be having this 2, I can pull it outside, and I will be having Im square upon 4 pi omega t minus sine 2 omega t upon 2, and the limits are from 0 to pi. So when you put the limit and when you do the calculations, IRMS will be coming out to be Im upon 2. So now again I know what is the value of Im. Im can be represented in the terms of Vm as well. Im can be represented as Vm upon Rf plus R2 plus RL. So Vm upon Rf plus R2 plus RL, and we will be having a factor 2 also over here. So this is how we can represent the root mean square current, right? So I hope you understood all of the parameters, you understood the basics of the half wave rectifier. If you have any doubt, you can put the doubt in the comment, and I will be trying to resolve your doubt as soon as possible. I hope you like this session. If you like it, please push the like button, subscribe to the channel, share it with your friends, and also give me your feedback. Thank you so much.